Okay, water acts as a universal solvent. So water is an important solvent forming many solutions with polar substances. So, I mentioned before that water is going to bind to anything else that's polar. So anything else that has that kind of positive and negative end. And what we see here in this picture is we see the formation of a solution between water and salt. And we see that the Na, the sodium part, has a positive charge, and the chloride part has a negative charge. So we can also see how the positive and negative ends of the water molecule will attach to them. So it has to be anything that's polar. You're not going to be able to make a solution with fat. So what is a solution? So I just used the term solution, but I didn't make sure that you know what a solution is, so now I will. So a solution is a combination of two things. First, we have the solvent, like water, and it is the substance that does the dissolving. And then your other substance, the solute, is the substance that gets dissolved. So in the example from the previous page, your solute would be the salt, the NaCl, and your solvent would be the water. And when you have them equally combined, then you have a solution. So when you have an equal amount of salt particles to water molecules to combine, then you have a solution. Now, the biological significance of solutions. There are, so many. But water is able to dissolve many substances and forms kind of like the building blocks of our cells. It forms the building block of our circulatory system. So inside of our cells, you can see on the left is a structure called the cytoplasm, which isn't just this jello blobby-like substance that helps hold everything together. There is a liquidy part of it called the cytosol, and there are chemical reactions that occur in this cytosol, including the process that begins the transformation of chemical energy into usable energy, which is ATP. That's called cellular respiration. But the first step occurs outside of a mitochondrion inside of the cytoplasm and everything. Us, bacteria, dolphins, everything. And then the other example there, our circulatory system, our heart, our blood vessels, and our blood runs on water. So if you see the picture there, first on the first test tube, we have the whole blood, and then we break that down into the plasma, and then the cell parts, the formed elements, and then we break that down even further. And you look at that plasma, 91% of that plasma is water. So we're just walking, sloshing solutions. Now, I mentioned that with a solution, you should have an equal number or equal amount of solute and water molecules. And what we could see here is what happens if you don't. So in each of these situations, the unsaturated, we would probably call unsaturated diluted, then we don't have as much solute. So there's more water. And if you look to the far right, a supersaturated solution is where we have more solute than water. And so this is probably something you've done in the past where you've put like a little packet of Kool-Aid or something into your bottle of water, and maybe it took a few sips of the water first before you put it in there. And then you had more solute, you had more Kool-Aid than you did water to combine with. And so it was kind of gritty because you always had that extra Kool-Aid precipitating out a solution because there was no water molecule for it to bind to. Now, there's a couple of things I'm going to have you add to the back of your sheet, and this is one of those. There's a little strip of paper that you'll get either from the sub or Miss Asbury, Mr. Agner, or Mr. Spivey, whoever is in that room with you, if you will please ask them for a copy of the pH scale, and the glue and the tape is still in the back of the room, and hopefully the colored pencils are on your table. So when you're talking about water forming a solution, you have to talk about the pH scale, the percent of hydrogen. So when a solute is combined with water, it's going to form hydrogen ions or hydroxide ions in solution. And what you get and how much of it will determine if you have an acid, a base, or if the substance is neutral. So I want you to take a few minutes and to color code this onto your little strip of paper that you get and glue that or tape that back to your notes, and then come back to me. I'll be waiting here in your Chromebook and Nearpod. Okay, so you're back. Now that pH scale runs 0 to 14, so it's a number scale. 7 is right smack dab in the middle, and that's neutral, and that is pure water. That's distilled water. Now, if you go below 7, then you have what's called an acid. And you've probably seen these little pH strips like you see in the upper right-hand corner there. If you use a pH strip, it's going to be looking for hydrogen ions and a hydrogen ion concentration. So acids, as you can see in the picture in the lower left-hand corner, produce a lot of hydrogen ions in solution. Now, the stronger acids are further away from that middle point, that neutral point of 7. So the farther down you go on your pH scale towards that 0, the stronger the acids become because they have more hydrogen ions. Now, if you look at some of the examples, some of the things that are mildly acidic are some of our foods that we eat. Yogurt is mildly acidic. Then if you look on down, let's say we start getting into the range of like stomach acid around the 3-ish. Sauerkraut. I don't know if anybody still eats sauerkraut. I would. Vinegars around a 2. Who doesn't love a good vinegary salad dressing? Lemon juice, 2.3. And then you get down to a 1, and there's your hydrochloric acid that will be toxic to you and can burn the skin. I have this little graphic here showing you the pHs of some of the drinks that we like. Me, myself, I'm a big fan of the Diet Dew, so 3.365. That's in the range of the stomach acid, which can range from 3 all the way down to a 1. There's a diet component to that. There's also like a genetic component to that as well. I also like the Diet Dr. Pepper, 3.169. So looking at all of these, they're in the range of stomach acid, except for mug root beer. Now, if you jump over to the opposite side of 7 and go above 7, then what we call these are bases, or you might see alkaline solutions. And a base doesn't have the hydrogen ions in solution. We're looking at something that OH negative hydroxide ions. And with these, just like with the acids, the farther you get away from that neutral 7, the stronger that the bases get. So if we look at some that are really mild, ocean waters around an 8, and then you start moving up to those household cleaners that have numbers on them to poison control, that if you ingest it or splash in your eye to call poison control. So you can see that household ammonia and oven cleaner, they're up there and they're pretty strong, and they can be just as harmful as acids, because extremes in acids or bases are harmful to the structure of your proteins, which rely on structure to function. And then I always just think it's nice to have a few examples of what we're talking about, but cleaning supplies are definitely some things that you want to keep your nose away from.